Well, hi everyone. I'm Fraser Cain, publisher of Universe Today. I have been a space and astronomy journalist for over 20 years, and sometimes I get a little over my head with the news, and I honestly have no idea what has been discovered. And it's times like that when I bring in a bigger brain, in this case, a doctor of particle physics. I believe that's what your technical term is, Dr. Paul Sutter. And he's going to come and explain a pretty interesting new result that was announced just, yesterday, 2 days ago?
Some point in the recent past.
Some point in the recent past. Yeah. All right. So first I need to give you a chance to introduce yourself as well. Who are you? What do you do?
Hey, I am Dr. Paul Sutter. I am an astrophysicist and theoretical cosmologist at the Institute for Advanced Computational Science at Stony Brook University and a guest researcher at the Flatiron Institute in New York City. I am also the host of several TV shows and the author of a few books with more on the way, and I write articles all the time, including for the esteemed publication Universe Today.
That's true. And you are essentially giving readers a master's degree in astronomy, one article at a time.
One jargon word at a time.
Exactly. Yeah. He's doing an Astronomy 101 course list of articles on Universe Today. I've got to say, though, I am absolutely loving the videos that you're doing with Ars Technica. Those are just fantastic.
Oh, thank
Three
you so
in
much.
now?
We're 3 in. We filmed all of those back in October, and we're releasing those. There are 7 episodes in our first season. This is a series called Edge of Knowledge, hosted by Ars Technica, and it is such a blast. Every single episode features an interview. I get to draw on the chalkboard. I get to play with props, which is hilarious.
Yep.
It's just so much fun, and the topics are all over the place. So we talk about Mars colonization. We talk about dark matter. We're going to talk about the origins of life and the future of climate change upcoming. It's such a fun series, and everyone go watch it so we get a second season.
And the production quality is really good. The level is nice because it's a little more tech. It's like, Ars Technica does a really good job of striking that balance, and so of just sort of not dumbing it down, but not getting overly technical. It's been perfect. I've really enjoyed all 3 episodes so far. In fact, I think Matt, I showed Matt the first episode. He's like, we're just gonna make a giant review, and so we actually did a big review on Universe Today on the first episode. So but we'll put a link in the show notes so people can go and check this out. And you've got to go watch this. Help Paul get another season of this, because I think there's more than 7 topics in the entire universe.
I mean, I hope so. I pitched to him 80.
Right. Yeah.
And we just took 7 of them for the first season.
Yeah. All right. So let's talk about the result. So what was announced again at some point in the recent past?
Right. So this is the result coming out of Fermilab, the Tevatron particle collider, and in particular, the collider detector at Fermilab, or CDF. They run all sorts of experiments, some version of smashing subatomic rocks into each other and seeing what happens after that. And this particular experiment that they've been running is measuring the mass of a particular kind of particle known as the W boson. And their result for this particle is that the mass of the W boson is a tiny bit heavier than what our theoretical predictions says it should be, and also heavier than what other experiments say the mass of this particle is.
Okay. So where does the W boson fit in the standard model of physics, particle physics?
Of life.
Life.
Where is W boson in your life picture?
How do I use it every day?
Yeah, it turns out you do. So there are 4 forces of nature: electromagnetism, gravity, strong nuclear, and weak nuclear. Each one of these 4 forces of nature has a set of carrier particles that carry or mediate this force from place to place. So for electromagnetism, we have the photon, which everybody knows and loves. For gravity, we're not going to talk about gravity.
Right.
For strong nuclear, there are a set of 8 particles called gluons. And then for the weak nuclear force, there are a set of three particles. These are the W plus, the W minus, and the Z bosons. And they get these different designations because the two W bosons have the same mass, but have one is positively charged and the other is negatively charged. And then the Z boson has no charge. And together, these three particles carry the weak nuclear force from place to place. So you can remember it, the W boson, W is for weak, it carries the weak nuclear force.
And what does it mean to say carries?
As in, if I want to have some interaction with, let's switch to another example that I think the audience will better appreciate. If I want to interact with you, Fraser Cain, electromagnetically, and if I want to sense your electric or magnetic fields, or I want to repel you with my electric or magnetic charge, I need to transmit that force from me to you. That there needs to be something that carries that force from place to place, that mediates that interaction, that allows that interaction to take place and to transport it over space and time. And these are the force carriers.
Got it.
And so when it comes to the weak nuclear force is like any other force. It can interact in very special ways. There are a list of rules that apply to the weak nuclear force. And to do the job of the weak nuclear force, if one particle wants to interact with another particle, through the weak nuclear force, they need to exchange a W or a Z boson, where one particle emits a W boson and it gets absorbed or interacted with by another particle.
Now, by my math, you said W twice.
Right. There are two W bosons, W plus and W minus. They have the exact same mass. They just have opposite charges. So in this news result, the news result and the headline just say, we measured the W boson, just one, but it has the exact same mass, either charge. So if you measure the positive charge or a negative charge, you're measuring the mass of the same thing.
And so what is the method that they use to actually measure the W boson?
For the most part, it's an indirect measurement. So the W boson, this force carrier of the weak nuclear force, as the name suggests, the weak nuclear force doesn't interact very strongly with other particles. It only happens in rare circumstances. We actually see it most commonly in radioactive decay. So the weak nuclear force is what enables radioactive decay to take place. And what the tevatron is doing is smashing particles together and creating a giant, messy soup, a shower of, or what they also call it, a jet of particles that come out. And these are all sorts of mixes of all sorts of particles that immediately start decaying and interacting and doing all sorts of complicated things. And within that soup, sometimes the weak nuclear force appears, transforms, radioactively decays one particle into a different kind of particle. We don't get to see the W boson itself, but an outcome of that process, of that decay process, is an electron. And electrons are super common. We're really good at measuring electrons. And so we measure the energy of the electron coming out. And then that tells us about the mass of the W boson. Because if you change the mass of the W boson, it changes the energy of this interaction and it changes the energy of the electron that finally comes out. So it's very indirect, but it's the only way we got.
And so what was the result that they came up with?
So they measured it. I didn't memorize this, so I wrote it down. They measured a W boson mass of 80,433 MeV over C squared plus or minus 9.
Right. So 80,000 plus mega electron volts.
Yep.
With a plus or minus 9. What? So that the 9, that's very precise though.
That's insanely precise.
Yeah.
That's like measuring your own weight to less than an ounce. And if you want that in grams, then you can just do that homework problem on your own.
Right. To within 15 grams. No, 30
There you go.
grams? 30 grams?
Something like that.
Yeah. Anyway, right. So that's fine. And I mean, according to the theory, the W boson was what? Roughly 80,000 mega electron volts?
Right.
Kinda?
I have this number too.
Yeah.
So we can theoretically predict what the mass of the W boson should be, and it should be 80,357 plus or minus 6.
So those numbers do not line up, and the error bars do not overlap.
That's the key difference.
Right.
Like this difference between the numbers in absolute terms is incredibly tiny. It almost seems like we're splitting hairs, but our measurements are precise enough that this is actually, these numbers are 7 standard deviations apart. And for reference, for everyone wondering about this MeV scale and all that, don't worry about it. The mass of the W boson is about 80 times heavier than a proton.
Right. And the experiment found that it was a little heavier than it should have been, according to all of the math in the beautiful cathedral that is the standard model of particle physics.
I wouldn't call it a beautiful cathedral.
The horrific octopus monster, intertangled octopus monster.
The shambolic, the duct tape and crazy glue and plywood cathedral that is the standard model.
Right. Okay. So then, we had a very similar conversation about a year ago with sort of a similar gist, which was somebody had found an interesting measurement in particle physics. And if I recall, your response was either they made a mistake or we don't understand the laws of physics as well as we thought we did. Yeah. Is it the same? Can we?
That's always our choices. Those are always the top 2 choices.
Right.
The issue, one of the interesting things about this measurement, it doesn't just disagree with theory. It also disagrees. The Tevatron is not the only particle collider in the world. It's not the only experiment that has measured the W boson mass. It is the only one, however, that has produced a result that disagrees with predictions from the standard model. So all the other experiments are consistent with the predictions from the standard model. And then we have this new Tevatron result that's sitting out here.
And I feel like one of the sort of wonderful things about science is that anybody who wants can build their own particle accelerator, run the experiment on their own, duplicate the results, and therefore that's how science progresses. That's how nature reveals its secrets to us one after the other. And so if they come out with a result that's dramatically different than essentially the result that everybody else has gotten, can't we just say then clearly they're wrong?
I mean, yeah, that's definitely an easy place to go in, and definitely something that the scientific community is going to dig in about this, because these particle collider experiments are very tricky, very precise. They contain, you have to get down to this level of precision, you have to really understand your instrument. You have to really understand the physics of the collider and all the analysis steps that go into that. You have to really, really understand this to a very high level of precision. And so it's not automatic that we should necessarily believe their uncertainty, because if their uncertainty was larger, if it was twice as big, we wouldn't care. There'd be no news result here because they would be consistent with the standard model. So really all the discussion, all the nitpicking, all the analysis is going to go into that plus or minus 9 to see if there's something funny going on there. Maybe there's a little bit more uncertainty here in the experiment than we had figured out, or we had deduced before. Or maybe that measurement, the average value, the 80,433, maybe that's biased a little high because of some quirk of the machine that we didn't take into account in the analysis.
It feels to me you've got a saying for this exact situation, which is, if it's interesting, it's probably wrong.
Probably wrong.
Yeah.
Yeah.
Would you describe this as interesting?
Yeah, this is definitely interesting. We know that the standard model of particle physics is incomplete. There is already a list of outstanding problems and questions in the universe that the standard model cannot explain. There are already weaknesses and incomplete facets of it. So that's not new, that there might be a crack in the standard model. The standard model already has cracks. But if there is something, a new crack or a new angle, something we thought we had known for sure that turns out to be wrong, well, this is potentially very interesting and exciting because it gives us a new hook, a new way to test and poke at the standard model from a new direction and potentially generate some insights and generate some ability to explain and push further and grow to be a standard model 2.0. But we're not quite there yet with just this one result.
And has anyone, I guess, hazarded a guess on why the number might be different than what is expected by the standard model, assuming it is correct?
Yeah. Let's take this Tevatron result at face value. Let's say all the other experiments that were consistent with the standard model, they had large uncertainties. Maybe they were just trying to get an answer that everyone agreed with. Now, let's say we fast forward 5 to 10 years. A bunch of colliders have turned on, they've released their results, and it does turn out that the W mass is higher than predicted. What this might be a sign of is that there's something funny going on with the W boson. And mass, you would think that mass, particle mass, is a simple thing and a straightforward thing, that there's just a particle and a mass is just one of its properties, and that's it. Like charge or spin. It's just this fundamental property. But it actually turns out that mass, the concept of mass, especially in subatomic particles, is this ferociously complicated concept. And the mass of a particle actually depends on how well that particle talks to all the other particles in the universe.
Right.
And so that's why when I quoted that the theoretical prediction, there was an uncertainty in the theoretical prediction,
yes,
which is a little bit weird. And that's because the theoretical prediction needs to take in the masses of like the Higgs boson in the top quark and run some analytic approximation schemes. It's actually this insanely complicated. You need a supercomputer to figure out the W boson mass. And so it ends up having an uncertainty of its own. And what this would tell us, if the W boson mass really is higher than we thought, it means that there might be some previously unknown entity in the universe, some unknown particle that is also interfering or intersecting or interacting with the W boson and giving it a little boost to its mass.
I mean, I think about situations like the neutrino problem and how the neutrinos were found to be changing flavors as they were leaving the sun. That's super weird, and no one ever ordered that. And yet
no one wanted that. No one asked for that.
Yeah, and yet it's a thing that seems to happen and took a long time for them to puzzle out. And so you're envisioning some situation where there is some other particle with very little mass that is somehow gumming up the results and getting in just as the measurements are being made. And that sounds like it'll be tricky to tease out that number, but that could
exactly.
Yeah, and that could explain, I guess, why they're getting a different result than other experimenters, just because the way the setup is, it gives more time for this other particle, perhaps, to get in there and mess up the results.
Yeah, they have a different setup. They also have a lot more data than the other experiments. They have a lot finer precision than the other experiments. So maybe they were just the first to notice it.
Right. So what comes next, do you think?
What comes next is that every single particle theorist in the world is going to publish at least 5 papers over the next 3 months. And so if there are 1,000 theoretical particle physicists in the world, then 3 months from now, we'll have approximately 5,000 explanations for why the W boson mass is higher than expected. And then we're going to wait.
Right.
So the Tevatron will continue collecting data. The Large Hadron Collider will continue collecting data. Other experiments around the world will collecting data. There will be more discussion and analysis around this topic for years, if not decades to come. This really is precision science that is slow, and it's aching, and it's backbreaking to get these results out. There's also going to be a lot of digging deep into the Tevatron data. If the Tevatron releases their data, then other groups might take their own attempts at an analysis, and they might get a different result.
Right.
There's going to be picking apart of their methodology of how they actually arrived at this, and there might be some flaw that could easily explain away this result. We need more science. That's what we need.
And the particle physicists are, and we've talked about this in the past many times, that it's all too perfect. Yeah, this horrific Cthulian nightmare from beyond space and time that is the standard model of particle physics does somehow seem to hold firm. All the puzzle pieces are in there, and no one can seem to find where the new puzzle pieces are, and yet gravity just keeps dancing around saying, you can't figure me out.
Mm-hmm. Yeah, there's issues. We can't explain gravity. We don't know what dark matter or dark energy.
Yeah.
We don't understand neutrino mixing, this property of neutrinos to change flavor. That is not a part of the standard model. And the W boson, what sticks out about this is that, yes, those are all unknowns. We get it. We don't understand that. This is a part we should have understood. There's something called a triangle in particle physics, where the Higgs boson, the top quark mass, and the W boson mass all connect to each other. So if you know 2 of them, then you can calculate the third. And this is like an important self-consistency cross-check for the standard model. So I can go do an experiment. I can get the Higgs boson mass and the top quark mass, and I can calculate the W boson mass. That should agree with experiments. And then if I go out and measure W boson mass and say Higgs boson mass, I should be able to predict the top quark mass, and that should agree with experiments. So all 3 of these should align up with each other, and any 2 measurements of any 2 should be able to explain the third. And this is a sign that maybe that triangle is a little bit broken. And this is something that the standard model is supposed to get right.
Right. And you can imagine then that maybe there are more particles involved in this triangle. It's more like a hexagon or a octagon with a bunch of other
very complicated relationships.
Yeah, exactly. Super interesting. Well, thanks, Paul. I really appreciate that. Again, if people want to sort of keep an eye on what you're doing, what's the best place to go and check out?
I would say 2 places: my website, pmsutter.com, or follow me on social media on all social channels, including TikTok, where I do not talk about the W boson mass.
I've got to subscribe to your TikTok channel.
At Paul Matt Sutter on all social channels, including
Perfect.
TikTok.
And definitely go to Ars Technica, do a search, and watch his series with Ars Technica. It's terrific.
Edge of Knowledge.
Edge of Knowledge.
It's so much fun. I had a blast writing and filming it, and the crew was amazing. It was such a wonderful experience, and it's a cool show to do, and I hope people learn a lot from it.
Fantastic. All right. Well, thanks, Paul. And next time something weird like this comes out, I'm going to definitely reach out.
You got it.
All right. Take care.